Hello, everyone. This is the lecture for section 4.1 and 4.2 of our Math 210S portion of the course, exponential functions. Okay, so we are going to jump into the next large family, almost the last large family of functions that we're going to be messing with for the class, exponential functions. So the two that we have left, exponential functions and logarithmic functions. Okay, today we cover exponentials. All right. Um, and then afterwards, right, in the next couple sections afterwards, we'll start doing calculus on both of them together, right? But first I have to define what the heck they are, right? And that's what this section is. I'm going to show you guys all what exponential functions is, okay? So first of all, let me define what exponentiation is, okay? Exponentiation is repeated multiplication, okay? And if you remember, right, back in grade school, right, when you said we were multiplying things together, right? That was repeated addition, right? So for example, if we had 3 times 5, right? There were two ways we can write this out. This was 3 plus 3 plus 3 plus 3 plus 3, right? Or we can write it as 5 plus 5 plus 5. Both of these are 15, right? Okay, that was the multiplication. That's how we defined multiplication. Okay, exponentiation is repeated multiplication. So if I write down 3 to the 5th, and that 5 is sort of like floating up to the right of the number, okay, this means I'm going to do this. 3 times 3 times 3 times 3 times 3. I'm going to repeatedly multiply 3 by itself, and I'm going to do it 5 times. Okay? And if I do so, right, you get 243. Okay? This is what exponentiation does. Okay? All right. Moving on. Okay? There are a couple rules that if you do exponentiation, right, you've got a couple rules here. 1, 2, 3, 4, 5, 6, 7, 8. These are 8 rules that you can sort of, if you define exponentiation, right? These are a couple rules that sort of follow readily. I'm not going to go ahead and I'm not going to prove them, right? But I will cover them here. Okay. The first one, the product rule for exponents. If the bases are the same, you guys see that bottom number is the same for everything, right? And you're multiplying two things that are to a power, right? Then you can add the powers. Okay? That's simple. This gives us this rule right here. Okay? The multiplicative distribution rule for exponents. Basically saying this, right? That if I had an exponent, right, I can give it to both of these separately and then put the multiplication in between. Okay? Okay. That is the multiplicative distribution rule. Okay? Quotient rule. Okay? Quotient rule states that if you have the same base, so notice that, right? That the A is the same for all of these, right? And you're doing 1 divided by the other, right? It's going to be the top minus the bottom exponent. Okay? That's simple. Okay. Next one, the quotient distributive rule. Okay? Basically the same as the multiplicative distribution rule, except we have a fraction. So basically saying, right, if you have an A divided by B to some power n, okay, then you can give the n to the top number and the bottom number, and then you still can keep the distribution or the division, right, and everything still works out. Okay? All right. Moving along. Power rule. Okay? Notice how this one is, you have something to an exponent that's also to an exponent. Okay? If this happens, you just get to multiply the exponents. Okay? All right. Oh, I wanted to keep that one highlighted. Okay, next one. Fractional powers rule. Okay. Uh, if you have something that has a like a weird square root thing, right? There's more than just one type of square root. You can have a cube root, a fourth root, a fifth root, right? If you can write it this way, that is equivalent to a fractional power. Okay. What people tend to remember when they write it in this way, right, is this. Hopefully, you guys see this, right? The n that's inside the square root goes on top of the fraction, right? And then the m that's outside the square root, right, goes on the bottom of the fraction. All of this, right, this whole thing right here is an exponent. That fraction is an exponent. So the better way, I know it's hard to write it. The Word doesn't do a real good job of showing this off, but it's supposed to be sort of like a big A to an n divided by m power up top, like that. Okay? Just to clarify some stuff. Okay, moving on. Negative powers rule. Okay? If you have a to some negative power, that is equivalent to doing 1 over the positive power. Okay? And then the last one, and this one's really just a, how'd I say this? Just to make the math work out. Okay? At least for now. Okay? Anything to the 0 power is always equal to 1. It doesn't matter what that a is. Okay? It can be 3, it can be 5, it can be 22, it can be negative 8,423. To the 0 power, always equal to 1. Okay. We're getting somewhere. We're getting somewhere. All right. Let's move along. Okay. An exponential function is anything that looks like this. Okay, the a and the b can be any numbers that we want. Okay, now I will restrict a couple of these. Okay, a, right, can be any number, right? A cannot equal 0. Okay, and b, I'm going to restrict it to be strictly positive. So it's going to be strictly bigger than 0. If you have it being less than 0, certain weird things happen. And we'll leave that to the mathematicians later if you ever study to be mathematicians. Okay. So we'll keep the b being smaller than 0 for later. Okay. All right. But now what I want to do is I want to study what both of these functions do. Okay. And sort of summarize what's going to happen, okay? And I'm actually going to, let's see if I can scooch one more bit. Yeah, there we go. There are two things that I want to cover that they're on the bottom. Linear functions, we know what lines are, right? They have what's called a constant amount change. So as your x sort of traverses the number line, right, you add or subtract a fixed amount, okay? And exponential functions, these are the new ones, right? They have what's called a constant percent change. A constant percent change. So what does that mean? So that's what I want to cover in this table that's going to be at the left. So on my table, I've got x values, g of x values, and f of x values. Okay, notice that the g of x is the linear thing, right? And the f of x is the exponential thing. Okay, so what I want to do is this. I'm going to go g of 0, right? This is how these functions work, right? Is 2 times 0, which is just 0, right? G of 1 is going to be 2 times 1, which is 2, right? G of 2 is equal to 2 times 2. This is how functions work, right? 4. G of 3, 2 times 3, 6, right? And hopefully you guys can see the next one's going to be 8, 10, 12, just how functions should be, right? At least a linear one, okay? Let's move on to f of x, okay? So let's do f of 0. 2, whoops, I don't need that, 2 to the 0. And we know from our rules, anything to the 0 power is always going to be 1. Okay? F of 1 is 2 to the first power, 2. F of 2 is going to be 2 to the second power, 4. F of 3, now here comes the hard stuff, right? 2 to the third. So it's going to be 2 times 2 times 2. That's going to be 8. Okay? F of 4, 2 to the fourth. That's going to be 2 times 2 times 2 times 2, 16. Okay? If you keep going, you're going to get 32 for the next one, and you're going to get 64 for the last one. Okay? Okay. So now I want to cover what happens between both of these. Okay? So notice when we start from here and we go to the next one, right? We started at 0 and we went to 2. So what we did was added 2, right? If we started here and went to the next one, we added 2 again. You can see what I mean by constant amount change? Plus 2. Plus 2. Plus 2. So you can see how this plus 2 is working out, right? It is increasing by a specific amount every time. It is increasing by a specific amount every time, right? A fixed amount at that, right? Okay, let's look at the other one. Let's say we start, oh, come on, there we go. Let's say we start here and we go bam, right? What did we do? We times 2, didn't we? Right? From here to our next point, we times 2 again, right? From here to here, we times 2 again, right? From here to here, we times 2 again. You guys see how this is working out? We're doing a multiply by 2 now, all the way down, right? This is the same thing as adding, right? And I'm going to put it in a different color so it doesn't get us confused here. I'm going to do it in green. Right, what we're doing here is we're adding 100% every time. Okay, we're adding the amount that was there before, right, to itself. So we're adding 100%. Okay, that's what it's meant by constant amount change. Okay. Uh-oh, my page is moved. There we go. Okay, now take a look at the graphs themselves. You guys see, so this is the exponential, right? You notice that that's growing now much, much faster, right? After this little section right here, after this section right here, right? The exponential is growing much, much faster, okay? As opposed to the linear, okay? And it turns out there's a fair amount of stuff, we'll see in a little bit, that requires us to look at these things exponentially rather than linearly, okay? To summarize sort of what's happening with them. Okay? All right. Moving on, I want to do some stuff with the graphs. So we have 2 graphs here. Okay? There is the red one. Okay? The red one deals with this. Okay? The red one deals with that one. Okay? And then we have a blue one. Okay? But that deals with this value, with these values. So for the first one, okay, let me actually highlight each one separately and talk about each one separately. This one Okay, the B typo. B has to be bigger than 1. Okay, whenever your B is bigger than 1, you have something that looks like the red graph. Okay, whenever you have a value C that's between 0 and 1, so something decimal, okay, something that's decimal that's between 0 and 1, you're going to have the blue graph. You're going to have this one, the one that goes downward. Okay, now what I want to show everybody is sort of how these things work. Okay, uh, let's talk about the red one first, right? So you see 0, 1, 1 b to the first, 2 b to the second, 3 b to the third. Hopefully you guys see how this pattern keeps going in this direction, okay? But it goes in the other direction too, so I can fill in these other points back here. So negative 1 is going to be b to the negative 1. Negative 2 is going to be b to the negative 2. Negative 3 is going to be b to the negative third. Okay? And then the same thing happens with the blue graph. Okay? That one has a pattern too. So you guys see over here, 1c to the first, 2c to the second, 3c to the third. They have a pattern there already, right? So that pattern can also follow, right? So c to the negative 1, c to the negative 2, c to the negative 3. Okay? Okay? Now, I do want to mention this. So hopefully you guys see this. Negative 3, 1 over b cubed. There's a rule that allows me to do this. Go check the rules up from the exponents from the very first page. Okay. The next point I can rewrite as negative 2, 1 over b squared. The next point after that I can rewrite as negative 1, 1 over b to the first. Okay, and likewise, I can rewrite my points for C. So for example, my other, this point up here, negative 3, I can make 1 over C cubed, and so on and so forth. Okay, this is just in case you ever need to graph these kind of functions. Okay, this is how they work out. This is it. All right. Now, what I want to do is summarize a couple things for all of these graphs. Okay. Hopefully you guys notice the domain, okay, for all of these functions, whether C is between 0 and 1, or C is greater than 1, right? The domain is going to be 0 to infinity. Oh, sorry. The domain is negative infinity to infinity. Okay? The two rules, right, that we can't break. We can't divide by 0, and we can't take the square root of a negative, right? In neither of these cases are we doing that. Okay, notice also that the graphs go from negative infinity to infinity. These graphs keep going that way, right, and that way, both directions. Okay, the range, that is 0 to infinity. Notice that both of the graphs, right, exist above this, above that, right, and that point right there is 0, 0. That's the origin. Okay. This both of these graphs, as they stand, they have horizontal asymptotes. Those horizontal asymptotes, y is equal to 0, always. Okay, which means, since all of this stuff is true, right, f of x is always going to be positive, and f of x has no x-intercepts. Okay, and notice that for both of them, right, the y-intercept, where it crosses the y-axis, is going to be 0, 1. It's going to be this magical point right here. Okay? All right. I covered everything I wanted to cover in terms of exponents. Now to show you guys how to sort of compute some of these, okay? And that needs Desmos, okay? So let me just, there we go. Let me just go ahead and do these really quick, right? How to, like, let's say you had a function. Let's say you had this, okay? I am asking to compute both of these, f of 2 and f of negative 2. So f of 2, 5, 3 to the 2 plus 1, okay? 5, 2 plus 1 is 3, okay? 3 cubed, 3 times 3 is 9, times 3 is 27. So this is going to be 5 times 27, okay? And that is, let's see what my calculator says, 27, 135. Okay? F of negative 2, it's exactly how you think it's going to be, right? 5, 3, negative 2 plus 1, 5, 3. So negative 2 plus 1, that's still going to be a negative 1, right? Now, here's a little bit of the rule, okay? 3 to the negative 1, that is equivalent to 1 over 3 to the 1 power. 3 to the 1 power is still 3, so I'm not going to even bother. Whoa, not what I wanted to happen. Sorry. I have all this technology, but when I hit undo, it wants to change the screen. 5 over 3. So this is how you compute it without using a calculator, okay? Now, Desmos can do all of these computations for you if you ever need to compute these, okay? The caret option, I think it's, let me take a look at my keyboard. It is option 6 will let you do exponents, or you can use the little keyboard that's at the bottom of every Desmos screen. Okay, now let's get into the good stuff. Exponential growth decay as a constant percent change. Okay, this should look familiar. This is the form of any exponential function, okay? When we start talking about exponential growth, when something is growing exponentially, right, there's a couple of bits of terminology that we need to pick up, okay? The A that we have up front, right, is what we call the initial or the starting value of our function, okay? And B is what we call the growth or decay factor, or the growth multiplier per unit x, okay? Basically saying that B is supposed to be whatever it's growing or decaying by, okay? We do have to do a little bit of cookup before we start using this, though. It's these two. So if your scenario, looking at a problem, right? If your problem says that you are growing, right, by a certain percent, then you are going to use this handy-dandy equation right there. Okay? If you are decaying, okay, if things are going away, right, then you're going to be using this one. 1 minus that percent. Okay? So what really needs to happen whenever you look at these kind of problems, right, you need to look at whether or not your problem, your scenario is either growing or decaying. If things are growing, right, or things are going away. Okay? So to illustrate a little bit more of this problem, okay, we've got an example for everybody. Okay, so I have here, the population of India was about 1.25 billion in the year 2013, with an annual growth rate of about 1.2%. Okay, notice that 1.2% is a growth, an annual growth rate. So we are guaranteed that something is going to be created here, right? Our numbers are going to go positive. Okay, so we've got 3 things to do: provide an equation, that models our situation. Okay. According to our model, what will be the population of India be in 2023? Okay. And last is use the graphing utility to find when the population will surpass 2 billion. All right, so let's do A. Okay. It's got to be our P of T, right? Has got to be some A times B to the T power. All right. Is my marker the thinnest? Yep, it is. Okay. Cool. All right, so this has got to be our form. This has got to be our equation. Yeah? Okay. Automatically, we can say that A, right? We need an initial amount. Okay. And we're going to go ahead and use this 1.25 billion as our initial amount. This is going to be 1.25. Our B, okay, it's a growth. You guys see that? It is a growth. So it's going to be 1 plus R in this case. We need our R. Our R is going to be our 1.2%. Now, we can't plug in 1.2%. We have to actually change it to a decimal. Hopefully you guys remember how to do that. We're going to grab the decimal point and go 1, 2 back. So 0.012. That is going to be the equation that we're going to need for our function. Okay, so P of T. Well, actually, let's do B first, right? So then my B is going to be 1.012. Our P of T is going to be 1.25 times 1.012 to the T power. This is it. Blammo. So this equation will model for us the population of India. B is asking us, according to our model, right, what will the population be in 2023? So the initial, right, T equals 0, right, that is the same as year 2013. 2013. Okay, so then if I need year 2023, right, that means T has to be 10. That's 10 years later, right? That's it. Now, at this point, it's plug and chug. So we need P of 10. (1.25), 1.012 to the 10 power, okay? Now, I'm going to do a double screen here. And I'm going to go ahead and show you guys the graph for it. And I'm going to show you guys how to compute the thing, okay? So I'm going to do P of T. There we go. P, capital P of X. Now, I can go ahead and change my variable. Hopefully you guys have seen this. I can grab the variable and change it to whatever I want. And for the most part, Desmos will do okay with it. You see that? And now I can put P of 10. And what we get out here is 1.4083. And this is billions of people, right? So in 10 years, in 2023, right, the population is going to be 1.408 billion people. Okay? All right. The last thing we've got to do, okay, and this is going to be part C, and that's why I needed to bring up the graph for it already. Okay, use a graphing utility to find when the population will surpass 2 billion. Okay, so then that means I want my Y value, I want my P of T value, okay, to be 2. Okay, Here's where my graph comes in, okay? And I'm going to go ahead and scooch that over. We see that it's going to be about, I need the y value, right? So I can grab my finger, I can grab my computer, and push this all the way till I get a 2. 1.96, 2.04, 2.02. There we go. About 39 years. You guys see that? Okay. About 39.5. And actually, I'm actually going to do that. I'm going to go ahead and plug in, right? I'll make it a point. 39.5, comma, P, big P of 39.5, just to get close enough. Okay, and I'm going to label it. There we go. And I'm going to grab my snipping tool now, wherever the heck it is. There it is. I'm going to clip that out. Okay. I'm going to paste it in. Whoa. Bear with me. I love technology, but good Lord, sometimes it's clunky. There we go. All right, so for now, we're going to just use an estimate, right? So then you guys see how that's the point right there, right? So I'm going to go ahead and do this. I'm going to do at t equals 39.5, right? P of t is equal to what? 2.002. That is close enough, right? But now, 39.5, that is 39.5 years after 2013. You guys see that? So we have to actually add the 39.5 to 2013. So then that means at 2052, right? There we are. And I should highlight my other thing too. This right here. Bam. Okay. We're getting somewhere. We're getting somewhere. All right. So what I have up for everybody next is some quick checks. You can try these on your own, okay? No matter what, though, I will be covering these in class, okay? So don't fret too much if they look complicated, okay? All right, moving right along. I am going to be jumping into a couple of applications of exponential functions, okay? The first one that I'm going to cover is a financial application, okay? And that is compound interest, okay? In the financial realm, there's a fair amount of stuff that can be had just by using compound interest, okay? This is the formula for compound interest right here, okay? Thankfully, all of these are just plug and play. You just need to know these couple of things right here. You need to know the P, the R, and the N, okay? And there's an N up there too, okay? So the P is just like before. I'm going to write this down below it, right? It's going to be an A, B to the T power, okay? This A value right here, right, is in the same place as that P. So it's still the sort of the initial amount, right? In finance, we say that's the principal amount, okay? And all of this other stuff, the 1 plus R over N to the N power, that is going to be our B value, okay? The R is the annual percentage rate expressed in decimal, okay? And the N is the number of compound periods, okay? And there's a bunch of them, okay? So for example, right, N equal 12, right? This is monthly. N equal 4, right? This is quarterly. N equal 365, this is daily. Okay, all of these have different usefulness in the financial world. So, for example, right, when n is equal to 12, that's monthly. This tends to be sort of like a loan. If you have a monthly loan or credit cards that you need to pay back, right, they tend to have n equal 12. Okay, if you're talking about finances for a company, right, there are these things called quarterly reports, right? They tend to work on n equal 4. Okay. Last, right? N equal 365. You'd think that there'd be nothing that would need 365 days worth of an interest compounding, right? But there is. Turns out, Uncle Sam, the IRS, if you miss your taxes, they are compounding your interest 365 days of the year. Okay, these are some, but not all. Okay, there's so for example, uh, uh, n equal 52. This might not look like anything, right? But there are 52 weeks in a year. Okay, so on and so forth. Okay, moving along. Let me actually bring this back up. There we go. Let's say I grabbed this entire equation right here, all of this, right? You guys see how the n can get as big as it wants to be, okay? What happens if I make the n go even farther than just daily? Let's say I wanted to do every minute or every second, right? Or every nanosecond that I wanted to compile an interest of some sort, right? What happens then, right? There is an actual value for it. That value is E. And this is the actual definition. This is the actual definition of that value E. There is a decimal representation, 2.71828 and da 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 da, right? But this is the definition. This is the actual way that a mathematician would write out the value E. Okay? All right. So now, why? Why do we have this? Turns out, uh, a a separate method of exponential growth and decay pops out. Okay, and this one's actually more applicable to all the other fields of science, not just finance. Okay, and this is what we call the continuous growth and decay function. Okay, these are going to spell themselves out whenever you need to work with them. Okay, so whenever you see something that says continuous growth and decay, you automatically go to this kind of function right here, AE to the RT. Okay. All the stuff is still the same, so let me write it again, right? A, B to the T. You guys see how that A is still that A, right? The B is going to be that E to the R, and then the T is going to be the T. Okay? Okay. The A is still our initial value, right? The R is the continuous growth rate or decay per unit time, whatever the heck the time is this time. Okay. It doesn't have to be yearly now. It can be by minutes, by hours. Okay. And that's what's so great about this formula. Okay. And then the T is going to be the elapsed time, whatever it is. It can be hours, days, minutes, seconds. Okay. And this is what's nice about this all. If your R is bigger than 0, then you have a continuous growth. Okay? If your R is less than 0, then you have a continuous decay. If you have it set up this way, right, then the problem itself tells you if R's got to be bigger than 0 or less than 0. You don't have to fumble around with the B equal 1 plus R or 1 minus R this time. The R is already, it makes a little bit more sense intuitively. If your R is bigger than 0, you automatically know you have a growth. If your R is less than 0, you have a continuous decay. Okay? And then, of course, there's still a financial application to all this, right? It's not right there, okay? The P is the principal amount, right? Or the initial amount invested. R is still going to be the growth or interest rate per unit time, okay? And the rules from above, these two, still apply. If your R is bigger than 0, you are growing. If your R is less than 0, you are decaying. That's it. Okay? All right. Like I said, okay, if you need uh, either one of these formulas, either one of these two for continuous growth decay, the problem will spell it out for you. It will say it's going to be a continuous growth, a continuous decay of blah, 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 blah. Okay? Okay. I got some examples for you. Okay. One of them, the first one, is a financial one. That deals with compound interest. And the second one, which we'll get to in a second, is the one that deals with continuous decay. Okay, so one of them needs the financial one, the 1 plus r over n to the nt, and the other one's going to need the e to the rt. Okay, but let's concentrate on the financial one first, the compound interest one. Okay, suppose you had $3,000 and it's invested at 3% and it's compounding quarterly. Okay, A is asking us provide an equation. B, convert the growth rate into yearly growth. C, use the equation you found in A. How much is going to be in the account in 10 years? And D is when will my account triple? Got it? Okay. Let's start with A. Okay. For A, provide an equation. Okay. We know that it's going to be a P of T equal some P 1 plus R over N. I'm just copying stuff down to the NT. Got it? Okay. We need P. Thankfully, that's already given. That's 3,000. Okay. R is 3%. We need to change this to decimal. All my percents I got to change to decimal. So this is going to be 0.03. Okay. And then my N is quarterly, right? So that happens so that means I need to do 4 of these in 1 year. So N is going to be 4. Okay, this is it. We're done. P of T is 3,000. 1 plus 0.03 divided by 4 to the 4t. Okay, that's it. B. I am going to convert it into a yearly growth rate. Okay, so you guys see how it says it's 3% compounded quarterly, right? I'm going to convert it so that it's just a b to the t. So I'm going to change my p of t function, right? I'm going to change it so that it's just a b to the t, okay? And to do that, I just need to grab this. Just this thing that's highlighted in blue, okay? So my b is just the 1 plus 0.03 divided by 4 to the fourth power. Okay? And I'm going to do it real quick because I didn't. To the fourth power. And what you get is this. 1.03033. So this means, right, B is 1 plus 0.03033, 3.03%. So if I am investing at 3% compounded quarterly, that is the same as investing and getting 3.03% compounded annually. You guys see that? So I converted it to a yearly growth. Cool? Cool, cool. Okay. C. Use my equation in A to determine how much the account will have after 10 years. This is exactly how you think it's going to be. I need P of 10. 1 plus 0.03 divided by 4 to the 4 times 10. Okay. 1 plus 0.03 to the 4. I'm just going to rewrite that exponent to 40. So 4 times 10 is 40. Okay. Now I'm going to show you guys the graph for it. Come on. There we go. Bam. Okay. So like before, I can grab this and I can go P of T equals, right now it's not going to give me anything, but if I do a T, there we go. There's our graph for it. Okay, and I can do now P of 10. In 10 years, I'm going to have $4,045.04. Yay, I made $1,000. $1,045. Whoop-de-doo, right? Boom. Okay. Question D, the last one for us. Okay. Use a graphing utility to find when the value of the account will triple. Okay. The initial amount, so I'm going to write this down here, D, right? Initial is 3,000, right? Triple should be 9,000. So I want my Y value for this thing to be $9,000. Okay. Grab that, put that there. My graph is not high enough yet, right? So I'm going to scooch this down a little bit. I'm going to scooch this in a little bit. And I want my Y value to be $9,000. So I'm going to start, there it is, 903, 911, what is that, 36.77? So I'm going to hide this so I can get a better view. It's hard. There we go. 36.8. So I'm going to put that as the point. So 36.8, comma, P of 36.8. I'm going to label the point. Now, I'm going to go ahead and take a picture of this right here. Okay? So we have it in our notes. Whoa. Blammo. Okay? Paste and make it tiny. There we go. I'm gonna we'll put it in our notes there. There it is. Okay. So by doing this, right, I'm going to go ahead and grab this and go over here, right? I can say in about, what's that going to be? 36.8 years. The initial amount of $3,000, right, will grow to $9,000. Okay. Yay. In almost 40 years, I'll grab $3,000 and turn it into $9,000. Whoop-de-doo, right? Okay, but this is it. This is what investments do. This is what banks do. This is what your bank account's doing on a regular basis. Okay. All right. Now, the next one is one that's a little bit more tied down to the other sciences. Okay. So in this one, notice what it says here. It's a continuous rate of decay. So I am saying that I need this formula. So I'm going to automatically go to A. Okay. I need A of t is going to be some A e to the RT. I automatically can assume, since it says continuous rate of decay, right? I have to write down the e to the RT this time. Okay. But this is just as easy a cakewalk as the one from before, right? My A, my initial amount is 150 grams. Okay. My R, let me put it right over here actually, is 1.5%, right? I can't plug in the percent. I have to change it. So 0.015. Okay. But this is it. We plug stuff in. A to the T, A of T, sorry, is 150. E to the 0.015 T. This is, oh, I already made a mistake. Notice how it says decay. Haha. You see, it says decay there, right? So then this means, since it's going away, negative 0.015. Okay. I almost ran with it. Can you believe that? Okay. This is the equation. Okay. Now, I want everybody to take a look at this, right? In the previous example, we did financial stuff, right? But financial is not the only application for exponential things. This is something from physics. This is something from chemistry. Okay. This is radioactive samples. We do have radioactive stuff around us, right? Okay. Next part. That was A. B. Convert the growth rate into daily growth. It shouldn't be daily growth. It should be, oh yeah, no, daily growth. Okay. So B. That means I need to do B equals E to the negative 0.015. Got it? It's just that portion. Okay? And if you compute this out, you get this. 0.985. So that means 0.9, sorry. 0.985 has got to be equal to the 1 minus some r. Since this is a decay, right, that r is that negative. Got it? So if you solve this out, you get that, let me not say equal. If you solve this out, r is going to be 0.01488. And if you change that to a percent, r is 1.488%. So if this is continuously decaying at a rate of 1.5% each day, right, then this is decaying at a daily rate of this right here. Got it? Okay, let's keep going. C. Using the equation that I found, how much radioactive substance will I have after 20 days? It's exactly how you think it is. So C is asking me to do A of 20. So 150 e to the negative 0.015, 20. Okay. I'm going to do it again. I'm going to grab our graph, bring that in. There we go. Okay. And again, I'm going to do A of t equal. Like I said, it shouldn't matter what you make the variable. Desmos, for the most part, will figure itself out. Okay. And then I can do A of 20. A of 20 is equal to 111.123 grams. So that's how much we have left. That's how much of the radioactive stuff we have left after 20 days. Okay. Part D. Wrong color. There we go, D. Okay. Use a graphing utility to find when the radioactive sample will decay to half its original amount. Okay. We started, right? So I'm going to do this. I'm going to do initial, right? That is supposed to be 150. That's how much we started with, right? So half, since we wanted to find out when it's half its original amount, that means we're trying to find when there's going to be 75 grams left. We want to find when there's 75 grams left. So I'm going to go ahead and double screen this again, okay? And we are looking when the Y is 75 grams. So what is that? Let's see. 77, 76, 74, 75. Oh man, there we go. 46.1 about. Yeah, so I'm going to draw that point in like I did before. So 46.1 comma A of 46.1. Now you can get a more exact point if you zoom in and all that stuff, right? But for now, since we're just messing around with how to appropriately graph this, okay, an estimate's all right, okay? And I am going to take a snippet of this using my, there we go. Bam. And I'm going to grab this and throw it into our notes. Come on, there we go. I love technology, but sometimes it's a little wonky. It's a little wacko. There we go. All right, so we got our point. Okay, let me make this a little tinier. Whoosh, and right there about. Yep, there we go. Okay, this is the point that we're looking for. Okay, so I'm going to grab this. I'm going to go up here, right? At 46.1 days, right? Days. The go 75, and just to know what the heck I'm writing, right? In about 46 days, a little bit over 46 days, the radioactive sample that we have, we started with 150 grams of it, right? That 150 grams will decay to half, to 75 grams of the original amount. Okay, and all of this for now, right? For both of the examples that I gave you just now, for both of these examples, we are only looking at sort of estimates. Okay, notice that I grabbed my graph, right? I grabbed the graph for this thing right here, and just sort of, tried to find something that's close enough. Okay, we will, in the next couple of classes, find out how to find these values exactly. Okay, but for now, use Desmos as much as you can just to find estimates. Good, solid estimates. Okay, just know what you're doing, first of all. Cool? All right. After that, let's see. After that, I've got some quick checks. This is going to take up the bulk of our time, hopefully. I've got a couple of examples for everybody. Everybody's going to do a financial example, and everybody's going to do a continuous example. Okay. If you want to try these on your own, that's fine. Go ahead. Otherwise, we'll do them during class. Okay. So don't be too nervous about it. Okay. And then what happens after that is lecture questions. I am donezo for this section. Okay. If there are any questions about this stuff, ask me during our quick check time. Come to my office hours or come to the math lab. I'm there nearly every day now. Okay. Besides that, happy studying.